I've got a new picture for this new part of what we were just doing with the velocity vectors, and we'll get to the next parts in just a second. But here's what we've done. We've taken these two velocity vectors and mapped those over. And another way to say that is, roughly, if I have a little rectangle, a little square like this, these would be two sides of the square, then what is that going to map to over here? Roughly, approximately. And that gets turned and scaled, but notice the angle between these guys is equal. That's kind of a special feature of this map. It's called being conformal. So that's one of the nicest pictures of the matrix of derivatives, that if I put in these two vectors, then the columns of the matrix of derivatives just give me exactly the output vectors, corresponding tangent vectors. So when I can show you a computer picture, I hadn't shown you a computer picture so far, but let's look at what happens if we get a computer to plot this. I'm using an applet that's actually for parametrizing surfaces, but it works just as well for these kinds of maps. Here's the domain, and I've put in s or t equals -1. I guess, yeah, it uses s and t. We'll call them v, u and v. V is -1 and u is 2, those two curves we looked at. And you can see the curves they go to. We already knew that they were going to be something like parabolas. All of these guys are these intersecting parabolas. And these two particular intersecting parabolas, if I look at the velocity vector of the blue curve, it goes off this way, and the red curve, it goes off this way, just like we have in our by-hand picture. And so even if we didn't have the computer to tell us this cool picture of these intersecting parabolas and the fact that they intersect orthogonally, perpendicular to each other, we could start to think about that and show that. And we'll get to that. We'll get back to that in a little bit. So let's go back to the by-hand stuff. Here's the next thing. Let me scroll down a little bit. What if, instead of looking at both the outputs and kind of looking at vectors and curves in the output space, but restricting the inputs to just one line or the vertical line or a diagonal line, what if we let the inputs vary in all directions and do things like take directional derivatives or gradients? A gradient is a great example of looking at what happens in all directions of the input, but then only pay attention to one of the output variables. One of the things that's nice about any transformation is if you want to get a little less geometric, but kind of down to simple stuff, you can just look at either the first output or the second output as totally independent functions. X of u and v and y of u and v are just functions. We happen to want to put them together geometrically, but you can all analyze them separately. So that's what this is about. For example, for some reason I chose the y coordinate first. I don't know. This is what happens if you map this function over, take the point, and then just see how high is it. Don't worry about how it goes horizontally. And that's a big loss of information, but that's okay. And so just take the y coordinate of the output of the transformation. What is its gradient? And I claim that is present in the matrix of derivatives. I guess I'll have to erase my nice picture, unfortunately, to get some room. So y of u and v is just this function. We've been doing that kind of stuff all the time. The gradient of y is just going to be the vector derivative of this with respect to u, which is 2v, and derivative of this with respect to v, which is 2u. Now notice I've been writing all my vectors as column vectors because they were supposed to be really geometric arrows in the plane, and those really ought to be column vectors. But for once, I actually wrote this as a row vector. And there's a reason for that, because look, it's exactly this row. Okay? And so for the gradient at 2 comma minus 1, for example, is just this guy. It's just minus 2 comma 4. And so in fact, the gradient, when you write it really carefully and you align it with this matrix of derivative stuff for transformations, the gradient really should be a row vector and not a column vector. And in particular, it's not really an arrow. You can fake it and artificially turn it into the column vector, minus 2, 4 as a column, and then draw that as an arrow in the UV space. But there's some really fake aspects to that. And so we definitely do that. It's definitely useful, but there's something a little troubling about that. And when you get to more advanced courses, you stop doing that, at least in geometry. So what about this question? Suppose we only care about the x-coordinate, how far left or right our target point ends up. Well, then we could take the gradient of x at 2 comma minus 1. Well, that's exactly the derivative of this function with respect to u and v. That's exactly where these came from. And so it's just exactly the row, okay? So the gradients of the individual output functions are the rows, and the columns, remember, were the images of the arrows. Those were where the U arrow and the V arrow went to. Those two facts are really good to know about the matrix of derivatives, okay? Now, here's a little more sophisticated approach to the matrix of derivatives that doesn't insist on splitting it up into either rows or columns. That's the only drawback of what we've done so far. Okay, so we know that f of 2 minus 1 is 3 minus 4, and we want to know where is approximately. Suppose I go off in an arbitrary direction. I add a little vector delta u comma delta v, okay, to my input. And what is that approximately? Let me just do a real small sketch map here. So I'm at this point, and I just walk away to some nearby point. And I want to say, okay, here's my output. Okay, how does that change the output point? A small change in input should correspond to a small change in output, and I want to predict approximately what that change is. That didn't erase very well, did it? Okay. Well, let's just realize that this is x of 2 plus delta u minus 1 plus delta v, and y of those guys. Just like what we were doing just a minute ago, separate them out into two one-variable functions. It'll be nice when we combine them in the end to get the geometry, but right now it's just two separate one-variable functions. Okay, but we know how to do this. We know how to do linear approximations. Well, this is just an equals, really, of some function like f, usually called f or g or something like that, of base point plus small changes. That's exactly where partial derivatives come in. It's first of all is just x of 2 comma minus 1 plus, then we take the partial derivative of x with respect to u and we multiply it by delta u. And let's see if I can fit it. Partial derivative with respect to v times delta v. So that's what we get in the x variable. It's getting kind of small, isn't it? I'll try and make it a little better here. In the y variable, the same thing. We calculate whatever that function is, y of u and v. We calculate it at the base point, plus how sensitive is it to the u variable times how much the u variable is actually changing, plus how sensitive is it to the v variable times how much the v variable is actually changing. Okay, so shoot, I want to keep that. Well, no, I'll bring it back in a minute. Okay, so let's separate that out. This is just the base point. X of 2 minus 1, y of 2 minus 1 was just the base point that was 3 comma minus 4. Plus, and now look at this. Look at the rest of it. This is exactly matrix times vector. It's exactly the matrix of derivatives times the vector of the changes in u and v. This is very, very much like what I was doing. It's essentially the same thing. What I was doing with this one, where we had an arbitrary vector, not just the u curve or the v curve, and we wanted to figure out where did that go to. It was a mixture of the blue and red curves, to use the pictorial terminology from the start of this part of the video, and that went to a certain mixture of the output blue and red curves. Okay. And now we're just doing the same thing and thinking of it as in terms of linear approximations. Okay. And so this is really, in a way, this is the most basic fundamental interpretation of the matrix of derivatives. It is the gadget that encodes the best possible linear approximation to f near this input 2 comma minus 1. I just take what I get at the base point. I always have to add that in. And then I take how far I walked away in the input variables. That's a vector, a column vector, in fact. Multiply it by this matrix of derivatives, and I get how much y delta the x and y change. So in fact, this part alone is the delta x delta y. Or it's really roughly delta x delta y. If I put dx and dy, it would be exact. So it's the idealized infinitesimal change. Okay, so in this case, it's just going to be, I can't squeeze it down there. Oh, man. Sorry about that. This thing sometimes, the gooseneck here kind of fades out over time. Okay, so let me just summarize that. The actual change in the target point, delta x delta y, that's impossible to get exactly from these kinds of methods, but it's roughly the idealized change in the target point, dx and dy, and that is equal to the matrix of derivatives times the input changes. And you can call it, remember on the inputs, you can call them d or delta, it doesn't matter. Okay. But when you're using d's on one side, it's kind of nice to use d's on the other. That is a very concise statement of how the matrix of derivatives helps us. Some arbitrary change in the input, feed that through this matrix times vector, gives us the idealized approximate change in the output, what's called the first order change in the output. And roughly, that's the real change, but it's not exact. Okay, because we're basically assuming, we're pretending, just like in one variable calculus, a lot of it amounts to pretending a function is really identical to its own tangent line. We're pretending that f is a linear transformation. And I should be a little bit careful. A linear transformation plus a constant shift, because the origin doesn't go to the origin for f. But that's where that was the plus 4 minus 3, or the plus 3 comma minus 4 bit. But in terms of changes in the input variables and changes in the output variables, this is the essence of all differential calculus from AB, BC, multivariable, whatever, pretending that f is a linear transformation plus a constant shift. Okay, so that's pretty cool.